All right, buckle up, because today we're diving into some seriously mind-bending stuff.
Oh, yeah, this one's a doozy.
Holographic phenomenology via overlapping degrees of freedom.
Catchy.
I know. The title sounds like it came straight out of a physics exam, but trust me, folks, this deep dive is going to be wild.
We're talking about the possibility that reality, the very fabric of existence, might be a kind of hologram.
A hologram, like those things you see on credit cards.
Well, not exactly. The idea is that all the information about a region of space, like everything in this room right now, is actually encoded on its boundary.
So on the walls, the ceiling, the floor.
Exactly. It's like saying a 3D image is projected from a 2D surface.
That's pretty hard to wrap my head around. It makes sense for a hologram you can hold in your hand, but the whole universe.
Right. But here's the thing. This holographic principle, as it's called, clashes with our current understanding of physics, especially quantum field theory.
QFT, the theory that describes how particles and forces interact, right?
Yeah, and in QFT, information is tied to volume. The more space you have, the more information you can theoretically fit in.
But the holographic principle says, no, it's all about the area.
Exactly. So how do we reconcile these two seemingly contradictory ideas? That's what this paper is trying to do.
And they do it by basically rewriting the rules of quantum field theory to make it holographic.
It's a pretty bold approach. Instead of relying on string theory or something like that, they're working directly within QFT itself.
But how do they pull that off?
Well, they borrow a concept from the world of quantum computing called overlapping qubits.
Overlapping qubits, okay. Help me out here. What exactly is a qubit again?
It's the basic unit of quantum information, like a bit in a regular computer.
Right. Okay, so what makes these qubits overlapping?
Instead of imagining them as distinct points, picture them as blurry clouds that partially overlap with each other.
Blurry clouds. Sound a bit fuzzy if you ask me. How does that work with a quantum field, which is all about particles and waves?
I know it's a strange concept, but bear with me. Let's take the example they use in the paper. A Weyl fermion field.
Okay, so this is like a specific type of quantum field.
Yeah, you can think of it as a collection of these overlapping qubits. Each qubit represents a specific momentum state of a particle, like an electron or a neutrino.
Got it. So instead of each particle having its own little space, they're all kind of mixed up together.
Exactly. Their information is no longer completely separate. It's like each particle has a footprint that overlaps with others. And the amount of overlap, that's the key to making the holographic area law work.
Okay, I'm kind of seeing the picture, but I have a feeling the math behind all this is probably pretty intense. They mentioned something called the Chow-Reichert-Sutherland-Wittig embedding.
RSV embedding, yep.
It involved like randomly chosen vectors and Clifford algebra. I'm starting to feel a little out of my depth here.
It definitely gets into some heavy-duty math, but the core idea is this. The CRSV embedding lets them cram all the information from these overlapping qubits into a Hilbert space.
A Hilbert space.
Yeah, it's a mathematical space used to describe quantum systems. And the key here is the Hilbert space they use is way smaller than it should be if those qubits were independent.
So it's like they're compressing the information of the quantum field, forcing those qubits to get up close and personal.
You got it. And it's this forced intimacy between the qubits that leads to some pretty mind-blowing consequences, like, wait for it, plane waves that decay.
Plane waves decaying. Hold on, plane waves are those, like, fundamental waves that go on forever, right?
In a standard quantum field, yes. But here, those waves actually decay over time because of all this overlapping business.
That's wild. So it's like ripples in a pond that just fade away.
In a way, yes. The paper actually derives a formula for this decay time, and it depends on the wave's energy and what they call a UV cutoff for the theory.
A UV cutoff. Another new term.
Think of it like a limit on how high the energy of a particle can be in this model.
Okay, so the higher the energy, the faster the decay.
Yeah.
But does any of this actually have real-world consequences, or is it all just theoretical?
Oh, it definitely has real-world consequences, especially when we look at things like high-energy neutrinos traveling across vast cosmic distances.
Neutrinos, those super elusive particles that barely interact with anything.
Exactly. We've detected neutrinos coming from incredibly far away, from objects like blazars.
Blazars, those are.
Supermassive black holes shooting out jets of energy.
Right. So how do these neutrinos and blazars connect to the UV cutoff?
For those neutrinos to survive that incredibly long journey from the blazar to us, the UV cutoff for neutrino physics has to be surprisingly low, according to this holographic model.
So the fact that we even see these neutrinos means what? The universe is secretly a hologram.
It's one of the mind-blowing implications, yes.
Yeah.
And what's even more remarkable is that this low UV cutoff doesn't contradict existing experimental data from neutrino detectors like IceCube.
So it's possible that holography is already subtly influencing what we're seeing in our experiments.
It's a tantalizing possibility. It's like holography has been hiding in plain sight all along.
This is all very cool. But if those plane waves are decaying, does that mean reality is slowly dissolving? Should we be worried our coffee mugs are going to disappear?
That's a great question, and it gets to the heart of what this model is telling us about space, time, and information. And to really dig into that, we need to explore some of the other wild implications of this holographic idea.
Well, my brain is already doing somersaults trying to keep up, but I'm definitely ready for more.
Good, because this is just the tip of the iceberg. You know what really gets me about this paper? They don't just stop at the theory, they actually try to connect it to stuff we can observe.
Oh, right. They use data from those neutrino experiments, don't they?
Yeah.
I'm still trying to grasp the fact that we might be seeing holographic effects, like right here, right now.
It's pretty amazing, and it all comes down to that UV cutoff we were talking about.
Okay, back up for a sec. The UV cutoff, that's the maximum energy a particle can have, right? In this model, at least.
Right, and the higher the UV cutoff, the faster those plane waves would decay, remember?
Yeah, okay.
But here's where it gets really interesting. We've seen these super high-energy neutrinos traveling ridiculously long distances, like billions of light years.
From those blazars, right.
Yep. And if the UV cutoff were too high, those neutrinos would decay before they even got close to us.
Ah, I see. So the fact that we see them at all puts a limit on how high that cutoff can be. It's like the universe is setting a speed limit for information.
Exactly. And that's where things get really cool. To explain those neutrino observations, the UV cutoff for neutrino physics has to be way lower than we thought.
Lower than what?
Much lower than even the Planck scale, which is like the ultimate energy scale in physics as far as we know.
Whoa. So holography is making us rethink some really fundamental stuff about energy scales and new physics. It's like we're getting a glimpse behind the curtain of reality, seeing a deeper level of structure.
I know, right? And the coolest part, this lower UV cutoff doesn't mess up any existing data. It fits in perfectly with what we already know from particle physics experiments.
So holography might have been right there all along, just subtly tweaking things at energy levels we can actually measure. It's kind of like finding fossils, right?
What do you mean?
Like those early naturalists who dug up dinosaur bones, they were seeing evidence of a whole world that existed way before them. We're kind of doing the same thing with holography.
I like that analogy. It's like holographic fossils. But the big question is, what does all this mean for physics going forward? Can we use this to make new predictions?
Right, because a theory is cool and all, but it needs to do more than just look pretty.
Exactly. This holographic model, it's not just a pretty picture. It opens up all sorts of possibilities for new research.
Like what?
Well, this paper focused on that one specific type of quantum field, the Weyl fermion field. But what about all the other ones? Do they behave the same way? And what about the expansion of the universe? How does that fit into all of this?
Right, because we've been talking about this static model, but the universe is constantly changing, expanding, doing its own thing.
Exactly. And factoring that in could lead to some even weirder and more fascinating effects. Remember, we're just scratching the surface here.
It feels like we've discovered a whole new continent, and we've only just set foot on the shore.
That's a great way to put it. It's like we're witnessing a paradigm shift, Just like quantum mechanics or general relativity changed everything back in the day.
Speaking of weird stuff, you mentioned earlier that this model has some randomness to it, that stochastic element. What's that all about?
That's where it gets really philosophical. It connects to this idea of quantum Mereology.
Quantum what now?
Mereology. It's the study of how parts make up a whole, especially in the quantum world.
Okay, so how do random qubits fit into that?
It might be the key to figuring out how our big classical world comes from all that weird quantum fuzziness.
Whoa. You're saying that the way these tiny qubits interact could explain how we get from a blurry quantum reality to, like, solid objects and forces?
That's the idea. It's like the universe is constantly walking a tightrope between the quantum and the classical, and holography might be the balancing pole.
That's a pretty wild image.
Yeah.
So are we saying that the randomness is what makes our reality solid?
It's a possibility. This model gives us a peek into how information is structured in the universe, how both the quantum and the classical can coexist. It's a delicate dance.
Okay, I'm with you so far. But how do we actually test any of this? It's one thing to have a fancy mathematical model, but how do we connect it to real observations?
That's the challenge. The authors of the paper admit that their model is simplified. There's a lot more work to be done to develop it and make more specific predictions we can actually test.
So it's a starting point, but potentially a really groundbreaking one. It feels like we're on the verge of a whole new era in physics, where holography becomes as important as gravity or electromagnetism.
I think so too. The implications are so huge that even if some of the details need work, the core idea of a holographic universe could completely change our understanding of everything.
You know, it's fascinating how this holographic approach brings together all these different areas of physics. We've got quantum field theory, quantum computing, cosmology, even philosophy.
I know, right? It shows how interconnected everything is and how powerful it can be to think across disciplines. Holography isn't just about physics, it's about information, complexity, the very nature of reality itself.
It's a truly holistic approach to understanding the universe. The more we learn, the more we realize how much we still don't know.
That's what keeps it exciting, that drive to push the boundaries, to ask the big questions.
It's a journey worth taking, even if it leads us to some strange and unexpected places, like a universe where plane waves decay and information is smeared out across boundaries.
Exactly. That's the beauty of science. It constantly challenges our intuitions and leads us to a deeper understanding of the world.
Well, this deep dive has definitely done that. We've explored a universe where information is limited by area, where plane waves dissolve, and where even the vacuum has a fuzzy, long-range feel to it. It's mind-blowing. Right.
It's a universe that's both strange and familiar at the same time. It challenges our perceptions, but also invites us to explore its mysteries.
I'm definitely feeling that sense of wonder and a deep appreciation for just how intricate and beautiful the universe is. And also that feeling that we've barely scratched the surface.
That's the spirit. There's so much more to discover. The holographic universe is a vast frontier just waiting to be explored.
Okay, before we completely lose ourselves in the holographic abyss, maybe we should dig into some of the more technical stuff from the paper, to really understand how they actually make quantum field theory holographic.
Good idea. We've talked a lot about the big picture, but the details are important too.
All right, folks, if you're ready for a trip into Hilbert space and Clifford algebra, buckle up. It's about to get even more interesting. All right, so we covered a lot of ground, blurry qubits, decaying plane waves, a fuzzy universe. It's a lot to take in, but I'm still a little hazy on how they actually make quantum field theory holographic. It's like, where's the math?
Yeah, it's one thing to talk about these big ideas, but the details are what really make it work. Remember those Fourier space shells?
Yeah, kind of. They're like layers in momentum space, right?
Yeah.
With particles of similar energies.
Exactly. And in a regular quantum field theory, each point in that shell, each specific momentum state of a particle, would be its own independent qubit.
But in this holographic model, they're squeezing all those qubits into a much smaller space, right?
That's the key. They force those qubits to overlap, to share information. They can't be independent anymore.
Okay, and that's where the CRSV embedding comes in, that mathematical tool they use.
Right, that's how they do the squeezing. It's a way of representing all those qubits with a much smaller set of mathematical objects. It's like a super efficient compression algorithm.
So they're creating like a zip file for reality.
Yeah, something like that. And the more they compress it, the more holographic the field becomes.
Okay, that makes sense. But how does this actually affect the particles? What does it mean for their information to be smeared out?
Well, imagine trying to locate a particle in momentum space. In a normal quantum field, it's a sharp peak, right?
Yeah.
But in this holographic model, that peak becomes blurry. It overlaps with other peaks.
So the particles themselves become fuzzy, like less defined.
In a way, yes. Their information isn't just at one point anymore. It's spread out over those overlapping qubits.
And that's what makes those plane waves decay, right? It's like they're not so solid anymore.
Exactly.
Yeah.
The overlapping causes the energy and information in the plane wave to kind of leak out to other modes.
It's a ripple that just kind of fizzles out.
A good way to think about it. And how quickly it fades away, that decay rate, all depends on that UV cutoff we talked about.
The higher the cutoff, the faster the decay, right?
Right. And that's how those neutrino observations from those crazy faraway blazars come in. They tell us the UV cutoff has to be pretty low for those neutrinos to survive the trip.
So those neutrinos, they're like little messengers telling us that the universe might be holographic.
It's a pretty mind-blowing implication. And it all fits in with what we already know about particle physics. It doesn't contradict anything.
Wow. It's like holography has been hiding in plain sight this whole time, just subtly influencing things.
That's what makes it so exciting. It's like we're just starting to uncover this whole new layer of reality.
Yeah, it's like, I don't know, we've gone on this incredible journey from blurry qubits to decaying plane waves to a universe where information has a speed limit.
And it all started with the simple question, what if the information about a region of space is actually on its boundary?
It's mind-boggling
Oh,
and a little bit terrifying, to be honest, but mostly mind-boggling.
I know what you mean. It really makes you question everything you thought you knew about the universe.
And the best part is, we're just getting started. There's so much more to explore, so many more questions to ask.
That's the beauty of science, isn't it? The journey never really ends.
Well, folks, on that note, we're going to have to wrap things up for today. But hopefully this deep dive has given you a new perspective on the universe and your place in it. Keep those questions coming, keep exploring, and most importantly, never stop wondering. Until next time.